I recently ran a small experiment in my English class. I was trying to find out whether implicit instruction or explicit instruction would have a bigger impact on students' English scores. I collected the scores, but now I'm not sure what to do with them. Should I use a T-test or ANOVA or something else?
Great question. If you're comparing mean scores between two groups or two time points, and your dependent variable is numerical, like test scores, a t-test is often the best choice. It helps you figure out whether the difference between two means is statistically significant or if it might have happened just by chance.
Okay, but I've heard there are different types of t-test.
Exactly. There are three main types. The one you use depends entirely on how your data is structured. Let's go through them using your study as an example. Let's say you had two different groups of students. One group received explicit instruction, and the other received implicit instruction. At the end, both groups took the same English test. Because you're comparing two separate, unrelated groups, the correct test to use here is the independent samples t-test. To run this in JASP, you first load your dataset and go to t-tests. Independent samples t-test. You'll drag the English test score into the dependent variable box and the instruction type, explicit or implicit, into the grouping variable box. But before interpreting the result, you need to check a few assumptions. Still in JASP, open the Assumption Checks tab. First, turn on Normality Tests and check the Shapiro-Wilk test for both groups. If both p-values are above 0.05, like 0.129 and 0.201, then your data is approximately normally distributed. Then, check the Levene's test for equality of variances. You'll see that under the main test table, if the Levene's test p-value is, say, 0.372, then you can assume equal variances and use the standard row of the t-test output. Now to the actual result. Let's say JASP shows T38 equals 2.21, P equals 0.033. Since the p-value is below 0.05, the difference in mean scores is statistically significant. That means the group that received explicit instruction performed significantly better than the group that received implicit instruction.
Okay, that's starting to make sense. What if I didn't have two different groups? What if I had the same group of students and tested them before and after giving them explicit instruction?
Then you'd use a paired samples t-test because you're comparing two sets of scores from the same participants. In JASP, you go to t-tests, paired samples t-test. You'll see two boxes. Drag the pretest scores into the first and the post-test scores into the second. Now, inside JASP, click the Assumption Checks tab and select Normality of Differences. The key thing here is that you're not checking if the pre and post scores are each normally distributed. You're checking if the difference between the two is normally distributed. If the Shapiro-Wilk p-value is, let's say, 0.068, then you can move forward with the t-test. Now, look at the t-test result itself. JASP might show something like T19 equals 3.88, P equals 0.001. Since the p-value is very small, you can say there's a statistically significant difference between the pre- and post-test scores. That suggests the explicit instruction made a real improvement.
Okay, so the paired t-test is only when I'm testing the same people twice, like before and after.
Exactly. One group, two time points, paired t-test. Two separate groups, independent t-test.
Got it. What about the third one? I think it's called the one-sample t-test.
Right. The one-sample t-test is used when you have just one group and you want to compare their mean score to some known or expected value. For example, let's say your school expects students to score around 75 on the English test. You taught a group using explicit instruction and want to test if their average score, let's say it was 78, is significantly different from 75. To do this in JASP, go to T-tests, one sample T-test, drag your test scores into the variable box, and enter 75 as the test value. Open the Assumption Checks tab again and check Normality Test. If the Shapiro-Wilk p-value is, say, 0.221, that means the sample data is normally distributed and you can proceed. Let's say the test result shows T19 equals 2.17, p equals 0.042. Since the p-value is below 0.05, you can say the student's average score of 78 is significantly higher than the expected score of 75.
Wow, I think I finally get it. The type of t-test I used depends on whether I'm comparing two groups, 2 times points, or one group against a standard.
Exactly. You don't choose the test based on the topic. You choose it based on how the data is structured. Once you know that, the rest falls into place, and JASP helps you check all the assumptions step by step.
But the result seems a bit weird. Isn't it usually better to learn a language in natural situations? That's probably why English immersion preschools are so popular. So why did the result turn out like this? Wait, could it be that even if the teaching method is the same, the effect changes depending on the learner's age? I should try checking this with statistics. Let's say children, teenagers, and adults all learned English using the exact same method. If I want to compare how fluent each group became, I could run a t-test between each pair of groups, right? So maybe 3 t-tests?
Hold on a sec, this is an important part. The t-test only works when you're comparing 2 groups. If you do 3 separate t-tests for 3 groups, the chance of making an error goes way up. Basically, there's a higher risk that you'll find a significant result, even if the difference isn't actually real. That's why, in this case, what you need is a one-way ANOVA. It's a statistical method that lets you compare 3 or more groups at once. So instead of doing multiple tests, ANOVA checks whether there's a meaningful difference somewhere among the groups, all in one go. Let's look at a simple example. Say the average scores are children equals 70, teenagers equals 75, adults equals 82. That kind of matches what you were expecting, right? But hold on. We can't just assume there's a real difference based on those averages. We need to know if the difference is statistically significant, or if it could have happened just by chance. Here's what an ANOVA result might look like. Lots of numbers, I know, but the main one to focus on is the p-value. If the p-value is less than 0.05, that usually means the result is considered significant.
Oh, I see. The p-value is below 0.05 here. So just like with the t-test, that means the probability of seeing this result, if there were no real difference, is super low. So it's probably safe to say there is a real difference between the groups.
Exactly. But we're not done yet. ANOVA tells us that there's a difference, but not where the difference is. So next, we do a post-hoc test to figure out which groups actually differ from each other. And look at this. All the p-values between each pair of groups are below 0.01. That means every pair, children versus teens, teens versus adults, and children versus adults, all show significant differences. In this case, it seems like the same teaching method was most effective for adults.
Whoa, but why did the older group do better? Isn't it usually the younger the better?
Good question. This has to do with the interaction between a person's developmental stage and the type of learning method used. Children are generally better at picking up language implicitly, like through immersion or play. But adults are better at explicit learning, consciously understanding grammar rules and analyzing patterns. So, if the method used was more explicit, like textbook learning, adults may have had the advantage.
Okay, great. I may be getting the outline now. But I got confused over a recent survey that I conducted. I wanted to find out if listening to an all English lecture has a relationship with self-rated English proficiency. I got the data, but if I were to turn this into statistics, can I use the t-test or ANOVA?
Well, let's figure out the data structure. What is your variable?
First is whether the person listened to an all English lecture or not, and second is self-rated proficiency. I divided proficiency into 5 levels: very poor, poor, moderate, good, and very good. They are not like numbers we saw before.
Yes, it seems like you got 2 categorical variable. When we run statistics based on categorical data, and remember, categorical data only, we use a chi-square test. This is a non-parametric test we use to find out if there is a relationship between categorical variables. There are 2 types of chi-square test, and we choose depending on if there is 1 or 2 categorical variables. If 1, we use goodness of fit. If 2, and also remember, every variable must be at least 2 levels each, we use the test of independence.
So in my case, I can use the test of independence?
Exactly. Here's a JASP result of the data you gave. Let me explain precisely. When we conduct chi-square tests, we compare what you actually saw, observed frequencies, with what you would expect to see, expected frequencies. If they are big in difference, we say there is a significant chi-square result. So, go to Frequencies and click on Contingency Tables. I selected the options for you to interpret.
The p-value is lower than 0.01. It's clearly below our significance level of 0.05.
Yes, that means we can reject the null hypothesis, which is there is no relationship between listening to an all-English lecture and self-rated English proficiency. Therefore, there is a relationship between listening to an all-English lecture and self-rated English proficiency. Encouraging. If you want to boost your English proficiency or overall confidence, perhaps, then try listening to an all-English lecture. Expose yourself. Oh, and since this only looks at relationships, we cannot define one as IV and the other as DV. Would you like to look at how goodness of fit looks like for elaboration?
Yes.
This is an example data that found out the language app preferences of 60 students. They got to choose from Duolingo, Cake, and Speaking Max. In this case, there is only one variable with 3 levels, so we use goodness of fit.
So we use categorical data in running the chi-square statistics. Then is there another method if the variables are, in this case, all intervals, only numbers?
Yes, if you want to run statistics based on interval variables, you can run a test of correlation. Pearson correlation figures out the pattern of relationship between the 2 variables. Let's remember, there are exactly 2 variables that are continuous. They cannot be defined as independent and dependent, having a cause and effect structure, although they might be, like chi-square does too. If you want to find a correlation between categorical variables, use the non-parametric alternative, Spearman's row.
Then I think this study data can apply for the Pearson correlation. The question was, is there a relationship between the number of hours university EFL students spend watching English media per week and their English vocabulary test scores?
Exactly. The watching hours and test scores are both interval variables, but let's check our important assumptions, normality and homoscedasticity. Here is a JASP output for these 2. Can you read the results?
Well, the p-values for the Shapiro-Wilk test are both above 0.05, so they are normally distributed. If they were not, can we use the Spearman's law?
Yes, Spearman's row are used when neither of these assumptions are met. Non-normal, non-linear, or categorical variables. Anyways, We use Pearson R for this data because all the assumptions are met. Now, can you interpret this value?
Well, the p-value is below 0.05, so we reject the null hypothesis of...
There is no relationship between English media watching and English vocabulary test scores. The R value is also 0.8, which also states strong positive relationship. The more university EFL students watch English media, the higher their English vocabulary test scores will be.
I can clearly see that in the correlation plot too. I think I got used to correlation analysis, but now I keep hearing about something called regression. Is it different with just another way of looking at relationships between variables?
Great question. Correlation tells you if two variables are related, like how they move together. On the other hand, regression goes a step further. It helps you predict one variable based on another. Therefore, in regression, we treat one variable as the independent variable, the predictor, and the other as the dependent variable, outcome we want to predict. So, unlike correlation, regression establishes directionality and supports prediction, not just association.
Then, are there some types for this regression?
Yes. If you have one independent variable and one dependent variable, you can use simple regression. However, in case of two more than independent variables, which are continuous or categorical, and one dependent variable, you can utilize the multiple regression.
Then I have some statistics. Would this study be a use case for regression? I collected data from university EFL learners and want to see if their speaking test scores can be predicted based on their hours of instruction, age of onset, and motivation.
Perfect example. In this case, hours of instruction, age of onset, and motivation are independent variables, and speaking test score is a dependent variable. If you look at your JASP output, you can see three tables such as model summary, ANOVA table, and coefficients table. In model summary table, it tells you how well your model fits the data. R-squared value means the effect size, and it means 81.1% of variance in DV explained by the model. The adjusted R-squared on the right takes into account the number of variables and adjusts for those that are not useful, helping to prevent overfitting. ANOVA table tests whether the model significantly predicts the outcome. F value tells you about is your model better than a model with no predictors, null model? And if p-value is lower than 0.05 and also our p-value is less than 0.001, it means that at least one predictor significantly contributes to explaining the outcome variable. Finally, coefficients table tells you how each predictor contributes to the model. In this output, for each additional hour of instruction, the predicted listening score increases by 1.28 points. I think you can be wondered which predictor has a stronger effect on the listening scores. However, all independent variables are all in different unit, so it's difficult to compare. That's why we need to use a standardized B to compare relative importance across multiple predictors. In this output, we can tell a 1 SD increase in hours led to a 0.871 SD increase in listening scores. So, we can summarize that unstandardized B indicates how many points does score go up per hour studied. On the other hand, standardized B shows which predictor has a stronger influence.
Ah, I see now. That was actually pretty simple. Then before I run this regression, is there anything that I should check first?
Smart thinking. Before running a regression analysis, you have to check assumptions. For the simple regression, you have to check linearity, homoscedasticity, and normality of the residuals.
Can I check all of that in JASP?
Absolutely. In JASP, you can check linearity by plotting the data. Next, you can check homoscedasticity, whether the residuals all deviate in a similar way from the model. In this context, residual indicates the distance from dot to line, which tells you how much your prediction missed the actual value. If you look at these graphs, left one shows small residuals and it means a strong model fit. However, right one shows large residuals and a weak model fit. In JASP, you can check it by clicking Plots and Residuals versus Predicted option, Residual Plot. Finally, you can check the normality of the residuals by creating a histogram or a QQ plot of the residuals. However, if you do the multiple regression, you have to check more assumption that predictors are not too highly correlated with each other, which calls multicollinearity. In JASP, if the VIF value is lower than 5, you are safe with this assumption. To avoid multicollinearity, partial correlation is very useful when you're deciding which variable to keep in a model when predictors are highly correlated. Like this in JASP, it can remove the effects of other variables from both the predictor and the DV.
Wow, regression does a lot more than correlation. It actually predicts outcomes and gives direction.
Exactly. If the assumptions are met, regression is one of the most powerful tools in your research tool.